configuration that recording automatically starts. Looks like not. Yeah, the recording has started. So yep, let me turn off the video. I hope the bandwidth will be enough. Okay. So we will, as I said, I will upload charts before the class, worst case by Friday. So do take a look at them. And if I don't have certain questions answered in class in your chat, feel free to reach out. You can verbally mention them or put in the discussion forum. I'll try to monitor that on the Canvas side, but otherwise we'll keep it interactive. My plan today is to take you through the handout to kind of discuss the course plan. So what you see the first session, we have a topic, single system attributes, but let me switch to the handout first. You must have all received the handout from the operations team. Am I correct? Because I had sent it out. I hope it has been sent to all. If not, anyway, this will also be uploaded on Canvas. So what we do in Canvas is on the course page, you will have the modules and all the slides, all the lesson plans are given there. The handout is uploaded there as well. So in the DSE program, this is one of the systems courses. So in the other courses, you may take a look at the various data science, machine learning, etc. kind of courses. SDA is a course which focuses more on how do you, in the context of that you're doing some data analytics, how do you look at the systems aspect of it? Now, this has a lot of conceptual uh, content in terms of building the backend systems with some references to specific technologies. So we'll see as it goes along. There is another course called Big Data Systems where we make it more technology heavy in the sense examples of technologies like Hadoop, Apache Spark, and so on. But we will touch upon some of the actual tech stacks also in this course. But assuming you may not have taken a systems course earlier, we will cover a little bit of the conceptual side, independent of specific technologies also in this course. So I'm sure you may have taken a look at the course objectives and so on. I'll try to go through what the modules contain. So in terms of textbooks, there is a book by Kai Wang where we will refer to a few things, but there's an online version of this available. You can use that. Most of the time what happens is we will refer to various additional material in class. I'll give you links for them. There are also a lot of these papers that are attached. You'll see all these reference books, or rather, these are most of them are documents and papers. We will try to take content from there. So these are a good set, but outside these as well, I will keep sending you or kind of putting in the slide deck certain links and references that you can use. So for example, when we cover some of the open source systems, uh, let's say we look at CouchDB. So there is a CouchDB documentation that can be referenced from here. Or if you're talking about Google file system, I'll cover it in class, but you can take a look at some of the research papers on Google file system and you'll get more information there. Now, in terms, let's go through the topics before today's session. So this first module is kind of an introduction to the data engineering part, while we talk about the actual systems later, but first consider the various types of data, structure and unstructured. That's what we'll go through in today's class, right? Different types of data storage systems. I'll give you an overview of that. That's kind of the first module. We talk about certain access costs, memory hierarchies, the concept of locality of reference. If you have taken a course on computer organization, you may be familiar with this term because when you discuss hardware caches and processors, uh, the main concept is around locality of reference. But we will try to go beyond that and tell you how in most of these systems, uh, whenever you're dealing with data, you have to build some of these layers outside the main storage in terms of memory hierarchy. And the locality of principal plays a great role there in reducing the overall access cost. So we'll talk about some of that and take examples. Essentially, you're trying to look at how do you reduce latency for data access, right? So there are a lot of uh, basic concepts there we will go through. We will also talk about parallel distributed systems, some overview. Now, you may not have taken a course in parallel programming earlier, like if you're given a multi-core system, or if you're given a set of nodes on which you have to write a data analysis algorithm, uh, you need to know certain basics or programming paradigms for you to do that. So we'll first of all cover a little bit of motivation and parallel processing, and what does shared memory systems, message passing systems, what do they mean? Different strategies for data access, like when you build large scale data systems, you will have to partition data, replicate data. So we'll talk about some of that. And in terms of programming, we use certain libraries. It's not mentioned in this handout, but we'll use OpenMPI as a message passing library. And for shared memory systems, we'll use something called OpenMP for doing multi-threaded programming. So we'll take a help of a couple of libraries and show how you can write basic programs on a multi-core and a multi-node system. Remember, you are understanding the systems side here, right? If you're uh, writing an analysis algorithm and trying to scale it up on a set of machines, then the underlying system is a distributed system. So you should know how to program in this distributed system environment. So you should be knowing some language, Java, Python, C, right? You should be familiar with at least one of them so that you get to do this programming part. Of course, I'll give you examples in class. You can take that code, run it, even on your laptop or any other multi-node system, and we can modify that. That's about module 2. Module 1, right? Module 1 is about introducing you to uh, certain things about data engineering, talking about parallel distributed systems, and programming those. Then we will also get into a little bit more about systems architecture side, like how do you, when you have multi-node systems, how do you classify this? Something called Flint's taxonomy. You may have studied in computer architecture organization course. So we'll talk more about Flint's taxonomy in order to kind of categorize different kinds of these systems into what is called SIMD, MISD, MIMD, these kind of systems. You'll also understand certain software architectures in how your systems are built, like client server versus peer-to-peer. You will look at a lot of modern databases. They are actually built on the peer-to-peer paradigm, whereas some of the older ones are built on a master-slave kind of an architecture, like single centralized node that controls all the other nodes. So some of these architectures we will go through in module 2. Module 2 will also start looking at some of the performance attributes of systems. So when you, let's say, take a problem and try to solve it on a cluster, a set of nodes, you must be wondering that if I increase the number of nodes, is there any kind of benefit that is coming? So I have a two node system or even a single node system. I add one more node to it. I mean, you expect double the performance. You want to get your work done in half the time, but that typically doesn't happen. So there are certain laws that govern how you measure this kind of a scalability of a system. So we'll cover those laws here that try to give you some theoretical bounds on how much should you expect your machine to scale up if you add more hardware. So we'll talk about some of that. We'll also talk about as you scale and add more nodes, there's another benefit of adding more nodes into a system. It uh, it actually reduces the single points of failure. So if I have, you must have noticed that when you run a web server cluster, right? Why do you do a cluster? You first of all want to increase performance of your website. That's why you put in multiple nodes in the web server farm. But also it increases reliability, right? If one node dies, the other one can take over. So when you look at a reliable system, Then there are certain ways to measure reliability as well. So we'll come to some of those uh, metrics like mean time to failure, mean time to recovery. So we look at some of the metrics to measure that ballpark. Can you measure reliability of a distributed system? And where are the issues? I mean, can you increase reliability in a certain way? So we'll take a look at performance and reliability. That's basically part of the second module. Uh, Once we are done with that, this module 3 is focused on primarily data storage. So when you're doing data analytics, you have presumably a ton of data. You want to store it somewhere. Now, there are various types of storage. And as we do that, we will look at uh, file system kind of storage. A lot of distributed file systems are out there. Like Google has a something called Google File System. There is an open source equivalent of that called a Hadoop distributed file system, HDFS. So we'll cover one of those. They're very similar in architecture, so that if you encounter another distributed file system somewhere, you should be able to understand like how it works, right? So we'll take an example, one of them, and go into some depth. Then there are database systems, right? So if you don't want to have your storage as just a bunch of files, very large files in a cluster, if you want to actually store data in a database and query on it, you must be familiar with relational database management systems. Here we will introduce another type of database systems called NoSQL systems, not only SQL. And these are used for storing unstructured, semi-structured, more real life kind of data, right? And they're useful in many cases. So we'll take examples even there and go through. Now, there are many options: Google Bigtable, CouchDB, MongoDB, Cassandra. There are many examples. We'll take one of them and get a little deeper to understand how do these databases work, right? What are the interesting properties that they have? Now, one of the very interesting properties in this database is what is highlighted here called consistency models, right? So they will give you, unlike relational databases, they will give you lots of options. As an application developer on top, you'll appreciate that database that can give you various options depending on your use case. So if you want to increase scalability of your system, you want to build a very large scale website that can store lots of data and process lots of user requests, then one way to do that we would discuss is uh, relaxing the consistency model. Like, let's say users don't want to necessarily view the data in the same way when they connect to this database cluster. In the sense, I may not be able to see the latest data, but I'm still given access to an older version of the data in the system. Why do I do that? Because we'll see that it improves performance. Uh, it can help to kind of increase availability of the system, right? So even if some nodes have failed, even then I will not see that failure. But the downside is I may not see consistent data. So these modern databases we will talk about, very useful for data analytics. Uh, they kind of help you to relax these models, consistency models, and allow you to scale and be more reliable. So we'll talk about some examples there. Then, so that's the storage part, right? So if you scan this through once again, like we'll talk about single systems, multiple systems, their attributes, generally parallel distributed systems. How do you measure performance, reliability? How are they architected? Talk about the storage part in module 3, and the final module storage, the module 4 is, okay, I have stored data, I have a parallel and distributed system, I have a database that can scale. Now, how do I design my algorithms, right? If I have a data analytics algorithm I have to develop, what is my strategy to design this algorithm running on this cluster, accessing this data? So that's where we will spend time in module 4. Right? So we'll take certain examples there. Towards the end, I will go through certain examples of data mining applications. Let's say you have a clustering algorithm or a classification algorithm. How does it run on a cluster in a parallel form and access data? If you have to design a new algorithm in order to solve a large scale data processing problem, then what are the system side you should look at? Like, how would you design such a parallel program. So we'll talk about some of that in module 4. So that's what essentially this is. We are not going into specific algorithms and learning how to uh, kind of write analysis algorithms, but we are looking at the system side to see how to build the system and what should you take care of on the system side so that your algorithm works faster, right, or is more reliable. That is the whole intent of this course. Any questions? Feel free to jump in. Typically, we will do one assignment. There'll be a couple of quizzes, and of course, the midsem and the compre. Right? The assignment most likely is going to be it's going to be a programming exercise, not a paper and pencil design exercise. You may be asked to kind of given a set of nodes, kind of use what you have learned in class to build a system, right, where your data is distributed across multiple nodes, and you want to design a very simple algorithm, because focus of this course is not on the algorithm. Design a simple algorithm or a program which runs across multiple nodes and shows how data processing can be done. So we'll think through how to design that. Okay. Any questions? Let's take a few seconds pause to see if you have any questions on the content. Okay, there are some questions that have not scrolled up, so let me just go and take it now. Yeah, Pratik, I will upload this on Canvas. The assignment will be a group assignment. Typically, we'll do 3 people groups. Okay. The compre, whether it's 50 marks or 40 marks, we are yet to decide. We'll figure that out. All right. So topics for today. So we went through the course outline, the handout. Uh, essentially, this is a very introductory session. So we'll go through some elements of what kind of data are we talking about. Uh, since you are taking this course and you may be coming from different backgrounds, I thought it's useful to talk about uh, the different data science processes and specifically the roles. So depending on which role in the organization you belong to or you aspire for, your take on this course or other courses in the program may be a little different. So I have a few slides there so that you can understand there are multiple roles involved in a data science project. We'll talk about the storage structure of the data. This is where we talk about different types of data like structured, semi-structured, and so on, and what kinds of data stores do they map to. And then we'll talk about some of the data processing aspects, and finally about storage models, cost, and I'll take some examples of these various storage models. Okay. So before we get in a very high level kind of picture of what typically a problem that people try to solve, and I'd like you to do some homework and figure out other interesting ways people try to solve this sort of a problem. There are a lot of startups in this space which try to simplify this, and this looks like a very basic layering. So you at the bottom layer you have a whole bunch of data, right, and typically very large data sets, and you ask various questions of this data. And these questions look fairly simple, right? Asking certain statistics. Uh, let's say this is all sales transaction data or HR data, right? And you're trying to understand various correlations. You're trying to get a slice of the data and calculate some aggregate statistics on it. And then finally, you're trying to prepare some insights and present it in a visual form to the end user. Now, if you are trying to build a system, there are many problems you have to solve in this. Now, this you could look at as I put data in a relational database. I write SQL queries on it for each kind of question, and I use some reporting tool like Tableau and so on to visualize the data. That's true. But now think about this data to be a very large scale that you cannot fit in a relational database. Think of the questions you are trying to ask they are asked by not necessarily a person who understands how to write SQL queries. Think of an analyst who doesn't even know SQL. Now, when you use this complicated database in the backend, like this modern age NoSQL databases, the queries are even more complicated, the languages to query and not standard. Now, there is an issue in having a user frame these questions without the help of a technical expert. So you'll find there are certain companies uh, that work on how do you simplify this layer, right? So I ask you to kind of do some Googling and do some research here. There are a lot of companies that work on simplifying this interface that you can sort of bring an experience like a Google search, where I type in keywords, I type in some natural language kind of a sentence, and I can translate to backend queries in the backend and bring in the data. It could also be that I want to dramatically improve performance of querying in this layer. So for example, you have backend databases of different types, but when I ask a question, uh, then that gets translated to backend queries, but that is translated very, very efficiently. It uses a lot of in-memory techniques so that I can bring in data, cache it, and I can serve multiple user questions from that data. So a lot of work happens in that layer. And finally, of course, on the insights part of it, there are a lot of people that work on the interesting visualization part. Right? How do I take a data set and do pretty intuitive visualizations on top? So this is just one of the problems, right? One problem statement, but it's good to look around that in a system built end to end for data analytics. Besides the algorithms to create those insights, which maybe you cover in other courses, like you may build a new machine learning algorithm to get some insight from this data. But outside that, the system stack actually matters a lot, and there is a lot of scope of work in the data layer, in this question answer kind of a layer, to make it more user friendly or increase performance of that layer, and then on the visualization side of things. So this is just kind of an open-ended question to you to look at some products, companies in that space, and how they solve the problem in these layers. You will even find a lot of open source projects which kind of work in this middle layer. Okay, so first let's answer the simplest question of what is data, which uh, we should not spend too much time on, but essentially you're looking at a set of values that you kind of uh, collect and model somewhere, which could be qualitative or quantitative variables, like qualitative or categorical variables, which are essentially strings, or quantitative variables, which could be uh, numeric values, right? And you collect this about various entities and you have to store it somewhere. Now, given that you have more digitization happening nowadays, uh, I mean, especially because there are processes in the business are getting digitized, you have all this sensor, IoT kind of information. These are all sources of information. And this is leading to a huge growth. And this problem, that's why is an interesting one to solve now in terms of collection. How do you model it, right? Which also involves how do you store that data? And of course, the different interesting insights you can gather from it. What we will cover mostly in this course is uh, how do you model this data and where do you store, right? What kinds of data stores are there? What are the different types of data? And given that somebody has to write an algorithm, what is the compute platform you provide? So data analyze for useful insights, it's basically you're trying to kind of figure out some actionable information from the data, right? And uh, it could be as simple as summary statistics, it could be a complex machine learning algorithm you write on top, and then of course the visualization of the data itself. This chart is also fairly simple. I mean, the volume and uh, the variety of data is increasing pretty rapidly. One or two important things I want to point out here, because otherwise this is fairly standard, is don't look at necessarily new age applications in social media or other places to look at the the volume of data that is generated, like Facebook data at some time few years back used to be about 500 plus terabytes per day and with huge amount of variety. That itself is a challenge. But even if you look at more closed and enterprise systems, if you look at New York Stock Exchange kind of examples, even there uh, the data volume is pretty high. It's about a terabyte per day that data gets generated. So very different from social media data, right? So even there's a need of building systems which you will see are not necessarily so simple with the legacy technology in terms of how relational databases were built. If you look at even things in IoT space, I mean, this was an example from I took from somewhere where they were talking about jet engines. The sensor data generates about 20 terabytes per hour, right? That's a humongous data set to model and store. So if you look at any enterprise, let's take an example and to see the variety of data that you have to handle, because this will lead to our discussion on the types of data and the data storage examples. So if you look at a retail company, right? This could be an online retailer. You take the Amazon, Flipkart type of scenarios. Check on the kind of data that is collected now at the application layer, the systems layer, from the user experience layer. Many of the applications easily support about a million plus transactions per day across products and users. There is delivery tracking data that gets generated. So even if you do a transaction which generates one data point, one of the 1 million data points in a day, even that transaction would lead to a whole set of delivery tracking information uh, as the whole order goes through the system and the delivery to the end user is tracked. Then you have unstructured or semi-structured data coming in sort of through reviews, right? Text reviews across multiple channels, websites, social media, through customer support channels. Customer support itself provides a lot of uh, data which is in text form, in emails. Even your calls get digitized. Uh, Speech to text algorithms are used to create text or create annotations on your call logs. And then, of course, there is a ad click browsing data and so on. So you will notice this data is a mix of metrics or numerical data, time series kind of data, like time stamped numbers. It could be natural language text, could be semi structured data like logs, events, and multimedia data like videos, images, and so on. Right. So data variety itself is an interesting problem to solve. So what kind of data stores do you need that store these types? And you don't need to have one solution. It doesn't need to be that I have one database where everything has to fit in. That's why you see nowadays that there is a ton of database technologies, storage technologies out there, and you have to find a matching one corresponding to your use case. What do you want to store? Okay. What is this data used for? User profiling, operations efficiency metrics, like if you do delivery tracking information, customer support experience, some demand forecasting, product marketing. There's no end to it, and because this is sort of the only way nowadays to create competitive differentiators. So any company focuses a lot on uh, actually collecting, modeling this data, and developing use cases on top of it, because that's the only way to create differentiators at this point, or even retain your customers. That's the reason why these areas become pretty important. There are many more examples, right? Not necessarily in a retail situation. I just captured a few here. Now, when you look at this data, and we'll look at it further in terms of what types of data and what are the different storage models and so on. But before that, as you look at this analysis or the insights you're trying to get, there are various types of questions you want to ask of it, right? So typically people broadly classify these questions into different types of analysis. Now, they're typically called descriptive, predictive, prescriptive. There is a category called diagnostic as well that people talk about in literature, which is kind of an extension to descriptive. So descriptive questions you ask of data are typically about what happened. right? If you have some situation, you essentially want to detect that situation. So you're basically analyze data. You're analyzing data using some kind of descriptive statistics most of the time. So it's like about describing, summarizing, identifying some pattern that has happened. So if you put data in a relational database and query it for reports, most of the time it's about descriptive. Diagnostic is when people try to do a little bit more in terms of, okay, something happened, but why did it happen? So some kind of correlation of cause and effect relationships. So example, the customer sales dropped because you figure out from your data that at around that time, sales tax component of certain item category had increased, right? And you figure out by exploring the data, uh, you get the reason why this happened. So often people do root cause analysis, right, of something they detected. So that set of questions kind of maps to diagnostic analysis. Then if you go to the next higher level, predictive, that is trying to answer what is likely to happen. So if I have my sales transaction data, then I may want to predict sales in in the upcoming holiday season, and that kind of starts getting into some amount of data modeling. It's not just about writing a query on top. I have to build some sort of model on the data. That means you need to have a system which actually supports running some sort of a modeling algorithm in a distributed fashion on the data and giving the creating the model and storing it somewhere, right? And at runtime, you want to look up that model and do some prediction. So this set of questions of what is likely to happen falls in the predictive analytics category. And the last one is probably the more advanced, uh, called prescriptive. So essentially there you are trying to generate recommendations. You are trying to answer a user's question and tell the user what action to take, which means you must be analyzing multiple scenarios, right? It's like a what if. You want to analyze multiple scenarios and somehow using some algorithm pick the best outcome. And this is often the focus of most of the AI/ML projects, right? Being prescriptive in nature. So you definitely it involves some sort of modeling, but there is some sort of weighing you have to do among various scenarios, evaluate and take the and kind of order them in a certain way that you can suggest to the user this is the most likely action you can take, and this is second most likely, third most likely, and so on. Now, why I'm going through this is because if you understand these types of analysis, you will be able to understand when I have to build a system, then what kinds of requirements will it have, right? Descriptive systems or systems supporting descriptive analysis are probably much simpler on the computation side. Moment you do diagnostic, you can imagine that we are exploring data. It's not one query. I may have to kind of run multiple queries to figure out the correlation between different things. So this system may be a little bit more complicated to build. So if I go back to that example I had shown, I asked you to look at different companies. Imagine that here, instead of asking one question, you're trying to explore this data and trying to figure out why did sales drop in a certain month. You're trying to look at various things, explore the data. So you can imagine the interactive query load that will happen in the system. And there are various techniques people use so that it's not about running one query and making it fast, but actually running multiple queries uh, sequentially from a user standpoint and giving fast results so that you can explore data. It's not like I submit a query, wait for an hour and it comes back, right? So you have to interactively work with the data. It poses very different system challenges. So diagnostic queries are not are more complicated than descriptive kind of analysis. Right? So understand these differences. Given a question we are trying to ask from the data, you should be able to categorize them into these one of these four buckets. And then when you're looking at the analysis platform, so given these kinds of questions you will run off the data, you run it on some kind of platform we will design, right? That's what this course is about. Look at this platform side. Where do you run the analysis? And definitely this is a distributed platform running on multiple nodes. These are some examples of analysis platforms. So when you look at these questions you're asking, in some cases you will need some kind of a batch processing platform. Think of the this case, think of the predictive or the prescriptive case. Predictive case, clearly we said we had to look at some historical data, build a model, so that when you ask a question, I can answer the question maybe very quickly, but I have spent some time in my algorithm to go through historical data and build a model. Now, likely I will build that model in a batch processing manner. So I may take hours to build that model to answer a question which happens in a few seconds, right? So I must definitely look at certain kinds of platforms that actually have very high throughput. That means they can process a lot of data, but you don't expect that uh, the analysis algorithm that you run in this batch processing system will finish in seconds. It may take a long time, but definitely this is a number crunching kind of a process. It processes a lot of data, produces an outcome, but you're not looking at the response time or latency. It may take time. So we'll talk about Apache Hadoop, for example, is one of the examples of batch processing systems. Now, in many other cases, you may want some real-time input, right? I may actually, as data comes in, I may look up the model and give you an answer uh, very quickly in a matter of few seconds. So that because I need answers in few seconds. So think of a fraud detection kind of a system, right? As credit card transactions are happening in real time, I want to actually say uh, whether this looks like a fraudulent activity or not. So then that kind of analysis, you have to look at a streaming platform. So we'll talk about streaming platform in terms of some basic we'll cover in Spark towards end of the course. Then there could be platforms which are meant for writing good data analysis algorithms. So these help you to slice dice data, may help you to write pretty complicated algorithms on top with some library support. Like I want to build a recommendation engine, right? Um, on my retail site, I want to recommend uh, when customers buy items, I want to create recommendations for other items to purchase. And I want recommendations to come in pretty fast in the embedded in the whole shopping experience. Uh, Apache Spark may be one kind of platform to help you do that. Then there are kinds of analysis which, as I said, are more descriptive in nature, descriptive or diagnostic. So essentially, I have a ton of data. I want to run SQL kind of queries and explore the data, right? And ask straightforward questions which are more like uh, slicing data in various ways and calculating aggregates. So Apache Drill is an open source. Google has BigQuery. On the Apache ecosystem, there is something called Hive. So there are many analysis platforms which help you in this kind of a straightforward querying data in a more SQL-like fashion, and people use it for descriptive analytics. And then uh, on the storage side of things, like all of this is about kind of computation. If you look at the the storage side of the platform, then there is Cassandra, MongoDB, HBase. These are various technologies which, uh, as from the names you figure out, I've not mentioned in a relational database management system, right? These are all modern age analysis storage systems that are meant for analytics workloads. So we'll talk about these, but these are mostly NoSQL systems that kind of handle your data storage. Okay. So that was a quick introduction to the data side, but we will come back to this again as I talk about different types of data and what kinds of database systems we have to pick. But before that, let's cover quickly about different processes and roles, because this is just helps you understand where your interest lies, right? And whether you want to do more of the system side, are you more on the algorithm side, and so on. So this is, I'm not going to go through this in detail. I took a reference from the web so that uh, you kind of understand the whole data science process. Anyway, this you will be aware in the DSE program. Uh, there are many steps involved in a data science project, from setting up your research goal to data retrieval, data preparation, exploration, modeling part, presentation, automation. There are many activities involved, right? Uh, Let me look up more on the role side. So as individual roles in a data science project, let me blow up this a little bit. Now this chart I found interesting because it kind of talks about in a project the different kinds of people that are involved and what kind of expertise they bring. Uh, so it kind of shows your interest on either on the domain side or on the tech stack side, or do you have more of quantitative skills, right? So if you're, for example, somebody who uh, wants to understand the system side of things, you probably are not the person who does more of the math or the quantitative side. You may not have the domain expertise. Domain expertise means that, let's say you're developing this for a fintech solution, right, in the finance domain. Now you may not be a finance expert, but you understand the various databases, storage systems, compute systems, how to kind of build up your analytics application, right? Then you may be somebody who has the in-depth tech stack knowledge, but you have to work with people who understand the math better and also bring in the domain expertise or the subject matter expertise. Now, why I'm talking about this is when somebody takes this course, they are likely enhancing their knowledge either as a data science architect. These are the two kind of roles I put in bold. They're either here, right, or they are a data science developer. Now, I'm not saying that if you belong to any other of these roles, you should not be taking this course, because in my opinion, you should try to understand at an academic level the whole thing end to end, because this team has to work together. But essentially, you will do more and more on the systems side if you are belonging to the architect or the developer role. But if you're a data engineer, you have certain kinds of activities to do, right? Capturing, cleansing of data. Uh, if you are a business analyst, right, you may have a different role. So think of, let's go back to this, right? So as a data scientist, you will be probably the expert in the quantitative skill area. If you're a data science architect or developer, you're likely the guy to, or somebody to bring in the tech stack knowledge, somewhat that is applicable to the data engineer as well, because unless you know the tech stack, you may not be able to understand how to deal with the systems as you do data cleansing, data preparation. And then the subject matter expertise is it comes from the domain expert, right? And somebody who understands, let's say, the finance, insurance, and health industry, some of these domains, right? They bring in the use case and help you to understand what is the math problem to solve there. And then you work with somebody who understands tech stack to actually build the solution. So in this course, we are looking at more of this, right? The middle part. If you take the big data systems course, that goes more in depth into specific technologies in building this tech stack. Here in this course, we are looking at a little bit more uh, systems conceptual parts, which are technology agnostic. Like we will spend probably 1 or 2 sessions on Hadoop, one on Spark, but one session on NoSQL systems. But if you take the big data systems course, maybe in the next semester, if you take it, then there you spend 4 sessions looking at Apache Hadoop ecosystem. You spend 4 sessions looking at how to write Spark applications, how to build applications using Spark libraries, and so on. Right. So hopefully this kind of tells you where what we are studying here, which role it appeals to. That's setting some context. Okay, so let's get into the storage structure. Uh, Here we will talk about different types of data and correspondingly what kind of storage systems that may be more appropriate for storing this kind of data. So if you look at, so broadly speaking, you'd look at structured, semi-structured, and unstructured, right? So structured data is fairly known how people have dealt with it for ages. So if you look at any of the relational database management systems, pretty much they deal with structured data. I mean, they have been upgraded over years to support semi-structured data as well. Like you can have XML stored in Oracle databases, right? That's possible. There is something as a concept of blob storage where you basically put in a chunk of data into some attribute in a database table. But these databases are not meant for storing semi-structured, unstructured data. They've been kind of put on as additional features. Uh, they typically end up with a fixed schema. Now, if you look at semi-structured, then there you loosen up the schema a little bit. You can say that, look, I'm going to store data which there's some metadata, but not that every record is going to have the same structure. I can put in data which in one of them has 5 attributes, in another one there is 10 attributes, right? So that boils down to semi-structured. A good example is if you look at application logs, right? You write applications and you have on middleware, you see a lot of logs getting generated. You look at all these log analytics companies, right? Processing log data. They're all dealing with semi-structured data. And then on the other side, there's unstructured data, mostly text or images or video. Now, when you look at unstructured, your goal often is to actually create some structure out of it. So even though the data gets ingested most likely as unstructured, the goal of your system uh, often is to run some logic and extract some structure and model that in a semi-structured database. So if you look at this chart, often people find say 80% is unstructured. That's because your input is like that. But unstructured often doesn't stay unstructured. It probably gets into the mostly into the semi-structured domain. So this is more of an input distribution of data. When you encounter in any system analytics solution that you any analytics application that you build, your input maybe 80% unstructured, but your goal is to structure some parts of it. Some examples given here on if you look at sentiment analysis, right? You're essentially looking at social media content, which is unstructured. But the fact that you are running some algorithms to extract certain sentiments out of it, right, as metadata and store it somewhere, means that you're converting unstructured to semi-structured. If you're doing image analysis, if you're doing NLP, right, or conversational AI kind of things, you're essentially looking at text and you're trying to create annotations on top and extract some kind of structure and store it finally in a semi-structured database. If you look at search engines, same concept, right? You're looking at unstructured text documents and then you're trying to create indices, you're trying to create annotations on top, and that is semi-structured data. Okay, so some characteristics of structured data. Predefined schema. That's why you end up storing it in relational databases. And you basically have very well-defined CRUD operations on these records that you store. CRUD is create, read, update, delete. So you have SQL is a good example, right? On the right side, it shows you a table where I've stored structured data regarding employees, uh, and I can easily write, create, update, uh, read, delete operations on top, right? Very well-defined semantics. Also, and we'll talk about this more later, most of the relational or all the relational databases storing structured data uh, kind of as a part of the design have what are called ACID semantics. Now, what is ACID? Look it up. It's a very basic terminology. You will take it up later as well. But essentially, it's about running transactions on top. So when I access data, it is atomic. Whenever I read write data, it's consistent. I cannot mix two transactions. So you reading, me reading, both are isolated transactions of the data. And durable means once I write the data, it stays there. It's not that you do something and my data gets deleted. right? That never happens. Now, this you take for granted in most of the databases because you have come mostly, or we have all come mostly from the relational database world. But when you get into the semi-structured databases, unstructured databases, these are things that you have to remove from your mindset. You cannot assume that ACID semantics is true. Uh, we'll talk about more of this later, but the whole concept of uh, NoSQL systems is how do I get away from ACID semantics? So you may be storing structured data even in this modern age NoSQL systems, but you don't necessarily assume that the database gives you ACID semantics. So we'll talk about this in depth. I'm just introducing this to you that legacy databases will always give you ACID semantics. But that is something that you should not assume as we get into this whole data analytics world and different databases that we will use. One good thing about putting data in such a structured form in relational databases is you can provide very fine-grained security and authorization. So I can sort of create a policy saying certain type of users cannot get access to the salary attribute for employees, right? Quite possible to do. That's a good thing about some of these relational database systems. There are known techniques to scale these, but it lands up in it has only up to a point that it can go, right? So that's why in data analytics systems, you likely don't end up using an RDBMS because they can only scale up to a certain point. If you want to build a very large scale system that is meant for this data analysis, you will not be using this. And they are very useful, but they are meant for what are called systems of record. Like if you're running transactions, like a banking application, you want to store and maintain records of data and do transactions on it, right? And very strong consistency guarantees. Uh, then you end up using this. But uh, in the data analytics world, you may still get structured data, but because you want to scale and have different kinds of consistency semantics, we will not use an RDBMS. So we'll introduce other types of databases in this course, even if you're dealing with structured data. The second type of data that you will encounter is semi-structured. Here there is no explicit schema or schema definition. So data and uh, schema are kind of separated. Like I may not be able to define the entire schema beforehand before I ingest data. So think of a grocery store application, right? For online delivery, servicing, million transactions or million kind of buy requests per day, and different types of products getting entered. Different products may have different attributes. So there are databases where I could model this data very easily. Looks more real life because it may happen that my strawberry item here has reviews and has some expiry date, but I have another item where there's no expiry date, or people put in some junk data. I mean, there's supposed to be an expiry date, but it happened to be for a batch that I don't have an expiry date, so I've not entered it. But it should still work, right? My application should still work. So this looks more real time, sorry, more real life data, where you may have different schema, you may have some attributes missing in some records, and on the fly, I can keep adding attributes. So I have a new type of item I want to sell in the store. Maybe that item has a different attribute to add, right? So I could easily add it, but it will not break my system. This typically doesn't happen in a relational database world. So easy to add new attributes. It models real life data much better, right? Attributes for every record could be very different. I don't have to define schema beforehand. This is very kind of amenable to storing XML, JSON kind of structures. This is like a JSON structure. And more importantly, the modern databases that are meant for or designed for storing semi-structured data, this all this NoSQL kind of systems that we will study, by default support flexible ACID properties. That means they do not assume consistency. So we'll discuss this in great depth, because this is the crux of the difference between the legacy systems and these modern systems. Where so it could be that, look at this, for example, reviews, right? Now when I'm buying, selling strawberries, maybe I want to keep a count. Now this is not entered here in this attribute. Maybe I have a count of how many boxes of strawberry I have left, and whenever a user buys, I decrement that count, right? So it's an inventory. So maybe I need some amount of consistency there, because otherwise I'll order a box of strawberry and I think it is available, but suddenly that disappears uh, from the database, and my order is not fulfilled because data was not consistent. Like two people buying kind of overlapped, and I had the last box of strawberry left, so you got it, but I did not get it, even though when I purchased it was there, right? So I definitely need some consistency semantics. But think about reviews. There is a user who added a certain review of the boxes of strawberries. Now, whether the other users read the reviews at the same time that it, or just after it is entered or not, doesn't really matter. So I may have entered a review after buying this box of strawberries. I may have entered a review at 9 o'clock in the morning, but as long as at some point of time that review is made available to me, I'm happy. I don't have to actually keep refreshing my screen and read the latest review on the box of strawberries. Right? This is true for most social media applications too. I don't need to read the latest comment. So this is a great example where semi-structured uh, data or databases that store this kind of data have that flexibility. And the reason they introduce that flexibility is because they want to scale better. They want to make the system hide certain failures. So even if something failed in the backend, you will still be able to access your web page and read reviews. So this will be a significant topic of discussion going forward. So these kind of databases um, and kind of data models are used in what are called systems of engagement, social media applications, anything that is kind of web user facing, right? Typically uses uh, semi-structured data and corresponding databases that support semi-structured data. And on the final one, this is it's about unstructured data. This is even more real life, right? Video, voice, text, etc. But as I said earlier, you're always some attempt is to extract some structure from this data and store it as metadata. So at the lowest level, there is at least some pixel level structure, right? I have a 1024 by 780 size image. Each pixel has some values, right? About its color and brightness and so on. So it's still it's structured, right? At the pixel level. But other than that, even at a higher level, if you're doing a face recognition, if you're tagging features, if you're annotating some piece of text, this is about the structure you're trying to create from unstructured data. And they will get they will end up getting stored in the same kind of a NoSQL database. So NoSQL databases that we will study will mainly cater to unstructured and semi-structured data. You can also store structured data in it, but the nice thing is that the system will treat it as semi-structured. So it's not that you have to define the schema beforehand and fix a set of attributes for all records and assume that always data is consistent. You can relax all of that. So I would say that NoSQL systems are a little bit more general in handling structured, semi-structured, and unstructured data. So that's why we'll talk about more of these systems later in the course. Some use cases of unstructured data, which you must be quite familiar with, right? So I'm not going to go through this. So let's look at next the given these types of data, what kind of storage will you look at, right? In this class, I just want to give an overview of different types of storage and databases. Then we'll follow up in later sessions on details of those. So historically, you've been using relational databases, right? And whenever anybody encountered unstructured data, they would typically use a file system, right? Images, videos would be stored on the file system, not in databases. Now, what evolved gradually is there were these XML databases that were introduced. So most of the relational database vendors introduced XML capability or blob storage, where you could start storing semi-structured data. Then gradually object stores were introduced, especially for storing multimedia content, where you could actually uh, store, it's like a file system but with metadata. So I could store a file, like my image is a file, and I would uh, create some metadata around the image, and I'll call that an object. And the data store is an object store because the abstraction layer is storing objects. Objects are like, here is a binary data and associated metadata. That's an object. So this object stores became very popular as people started looking at multimedia storages, video, audio, and image storage systems. Now, since then, things have evolved more, right? If you look at today's scenario, if you're looking at structured data and it is relational in nature, that means your data needs to be modeled as a relational database. I will not get into relational databases. I hope you have enough background on it. Uh, Very simply put, these are databases where you kind of model data as multiple entities and relationships between entities. Like if I have a banking system, then I would have users, bank accounts as probably two different entities, and uh, I would kind of model relationships between them and attributes on the entities and the relationships. But these databases have been there for a long time, and they are used for nowadays also structured data where you need relations between entities to be stored. So things like Oracle, MySQL, MS SQL, or even cloud databases like SimpleDB on Amazon. These are all good examples of how you would actually get a relational database and store this kind of data. So these databases typically support ACID properties and you can do transactions on it, and data is always very consistent and so on. But they have limited scalability. And if you have semi-structured or unstructured data, or you have structured data but it's not relational, it's like I have a ton of data to store sales transaction information, but there's no relationship I have to store. It's like a flat big CSV file, but it's terabytes in size, right? It's structured, but I need a different kind of system. I don't need to use a relational database. So for this, there are options. So you can either have file system options to store this. So we will study Google file system or Hadoop distributed file system, right? Which can store some of this. There could be object stores. So if you look at Amazon's S3, that's a very popular object store that is there on cloud, right? If you are storing especially multimedia data, this is a great way to store, right? Or any binary data you want to store, object stores are good. Or there are all these NoSQL databases, right? MongoDB is a good example. We'll cover a little bit of that in class. Uh, we'll cover, I think, Dynamo as well, or one or two of them we will cover. So if you look at MongoDB, S3, uh, the Elastic File System, or HDFS, these are great examples of storage systems that can store semi-structured and unstructured data. So in this course, we will focus on on the second set of systems. We will not cover relational databases because even if your data is structured, these don't scale. And here we are looking at systems that are running data analytics use cases. They need scale, and most of the data that you will encounter in analytics use cases are not relational in nature. They're typically huge, large, flat files that of data that you have to bring in. So going down to the next level, right? So we talked about some of these databases. So these are your common data categories. So we talked about structured, unstructured, semi-structured, right? So this is the next level of detail from that. So if I look at any kind of data set given to you, uh, you will typically categorize them in at least kind of these 7 odd categories, and each of them will map to a certain kind of database. As I said, you may have structured data but relational in nature, right? This has been traditionally what data looked like in most legacy use cases. You must have referential integrity, which means relationships between entities, asset transactions, and you want to uh, predefine the schema before write operations happen. So many of the enterprise applications still use this, especially when transactions are needed. Then you will find a kind of category of semi-structured data, which are of type key value pairs. So you have an attribute and you have a value. That's how simple the data is. So there are many applications out there which need very high throughput, low latency reads and writes, and tremendous scalability. They typically look at key value kind of data models and corresponding data stores where you just want to store keys and values, right? There's hardly any relationship between even different keys. If you look at many caching systems like Redis and so on, they're essentially key value stores. If you look at your retail applications, many of the shopping carts basically use key value stores. When all what you need there to store is uh, what item, what quantity for a user ID, right? So it becomes very simple data schema. So product catalogs, these are good examples of key value stores or key value data models. Then you can have document data stores. Document data stores, think of groups of key values put together, right? So I want to store an employee record, and an employee record is a set of keys and values. If you go back to that example I gave earlier, I could actually create an employee document, and within that, these are my keys and values. Employee ID is a key and the corresponding value, name and the corresponding value, and so on, right? This could be stored as a document. So a document is equated to kind of a row in a table in the relational world. So there are document data stores. If you look at MongoDB as an example, we'll talk about later, that's a document database. Content management, many of the mobile applications use a document data stored in the backend. Then if you look at in-memory data stores, here you try to model data as much as possible in memory, and you would basically query by the key, and you want very, very minimum latency to retrieve the value. So instead of storing or relying on more of storage, think of a key value system that is built into memory. These are actually great for caching. So if I say Redis probably belongs into this. Then there are graph databases, which are the extreme case of modeling relationships. So if you look at a relational database, it models relationships between tables, right? But suppose if you look at social network data, now everybody is a user in a social media network, but all users are connected to each other, right, in some way. So it's very hard to model in a relational database because there's one big fat table called users, and it's like all the relationships are within the table itself. Like user 1 is connected to user 10, user 10 is connected to user 100, right, in a social network. So you're not able to separate out into different tables and connect them. So in that case, you end up using graph databases where it's very, very relationship heavy at an individual entity level. So social network graphs are a network of devices. These are good examples where you want to model in a graph structure. These are not only good for social networking, but they're also good for recommendation engine building, right? You want to explore connectivity between users and items and so on. They're great for fraud detection because you're trying to connect or discover relationships between various entities. So graph databases are also like NoSQL databases, but of a specific type. Another kind of structured data that you could encounter is time series data. Often when in IoT sensor use cases, you want to collect, let's say, temperature, humidity information from sensors and store it somewhere, right? Uh, or you want to do event tracking, you're building a monitoring system. So you will use a time series data model, timestamp and value, like a special kind of a key value store, except here it's timestamped. And then recently, ledger systems have become very popular, right? You've heard about blockchain and so on, right? Or hyperledger systems. So ledger systems are where you want to store data in an immutable fashion, and you want to, that means you never delete data, you keep adding to it, and you should have capability of verify changes, verify the history. So I should be able to do data lineage in that database. So I should be able to kind of store versions of data, and I should be able to track all the changes and verify the whole change record of that particular data item. These are great for uh, building systems of record for transactions, but you want them to scale, right? So supply chain or anywhere blockchain is finding use, uh, in the financial domain, healthcare, supply chain domain, these systems are becoming very popular. So this is one way to model data as well. So I've given you some examples specifically from one vendor. So if you look at AWS, then uh, these are some example cloud data stores, databases that you will find that belong to each of these categories. So I'm giving you this because it's good to understand different types of data, not just at a structured, semi-structured, and unstructured level, but also at this level of granularity, because this is how different applications will model data depending on the use case. Also, it helps you to understand mapping to at least one vendor's products to each of these categories, that you can look up these, read more about it. Some of them we will cover in class, uh, and you will know what to use in your application, right? As you're building a data analytics application, which one do you use? So I think Pratik, you asked about DynamoDB earlier. I did not answer because I was waiting for this slide. So DynamoDB is a key value store, right? MongoDB is a document store. We'll cover Elasticache in this class a little bit more from a caching standpoint. That's an in-memory data store. It can be implemented using Redis or Memcached. Graph, Amazon Neptune. There are other very popular technologies out there, so don't get restricted to only Amazon. I mean, this is just an example to show popular cloud options, but look at other vendors and equivalent products as an exercise. So Neo4j is a graph database that is very, very popular. You look at TimeStream from Amazon, Quantum Ledger databases. Now RDS is there for relational data, right? And within RDS also you'll find lots of options. Uh, RDS is kind of an overarching product, but under that you can choose whether to use a MySQL backend or an Oracle backend, right? You can pick and choose. But this is just an example. There are many other vendors. I leave it to you to do some research on what you use currently, what you know about, and which category does it belong to. You can easily find it. Okay. All right. So let's look at the next topic. So I'm gradually going towards storage models and the cost and the caching part of it, right? I mean, so the next topic to essentially take you towards that is understand a little bit more about data processing and uh, CPU memory bandwidth and how things are growing and how the processing capacity is growing at various levels. So I'll show you two charts. These are taken from your textbook, Kai Wang's book. This book is a bit old, so it's like a decade old stuff where it stops. But again, it's interesting to just look at the trend and not pay too much attention to that the dates stop at 2011. So I think there are a couple of things I want to highlight in the next two slides before we we go along and talk more about the storage models and the costing and so on. One is if you look at this chart on processor and network, and if you look at this growth, more or less following Moore's law so far, right? Uh, Essentially, Moore's law was stating that, especially on the CPU side, that the capacity on the processing power doubles approximately every 1.5 years or 18 months. Now, you will notice a lot of discussion going on regarding Moore's law not effective anymore. Doesn't It's an empirical, evidence-based law, right? It's nothing that you can prove theoretically. So uh, that due to various reasons, Moore's law is not holding anymore, or will not hold anymore. If you look at the next 18 months, now that's true, but that's partially true. There are ways to work around it, especially with this GPU-based systems coming in with multi-core, massively multi-core processing. It may still have workarounds, but essentially what you have to understand is we are getting limited by power, right? To make a processor faster and faster, and that's because of this relationship with frequency and voltage, right? You have to keep your voltage low, right? So that you don't go beyond the power budget. And as frequency is increasing, there's a bound on how much you can achieve. It's because this is a function of frequency and voltage. So you can't lower voltage below a certain level most of the time to make things work. So given this limit, you would end up building systems that cannot add more processing capability on the same board, right? So you have to start looking at how to create a system that consists of multiple nodes, multiple machines. And that is perfectly okay, because if you look at the network side of things as well, that has been following something like Moore's law over several years now, right? Link bandwidth has also improved pretty much 4x every 3 years, which is doubling every 1.5 years. So it's also keeping up in terms of network capacity increase. So it's not necessary that you build bigger, faster processors. You can simply build machines which are small enough and they're tied with commodity networks, and you can build a large scale distributed system, right? So the whole reason why we are talking about clusters and large scale distributed systems and huge clusters of distributed databases like NoSQL systems and so on is that you don't need to build a big fat monolith processor and run on it. You can build a distributed system, small nodes connected over the network, and that's a good way to scale because you're pretty fast network. And anyway, processors are not may not be following Moore's law in the future, or it may be expensive to follow Moore's law. You may have to use a massive multi-core GPU architecture to scale, but that is very expensive, right? So many of your data analytics workloads may not afford it unless it's a very critical application. So when we study Hadoop, Spark, these kind of systems going forward, you will notice that they are built on commodity machines, off the shelf hardware connected over Ethernet. Now, if you really have a very sophisticated deep learning based application, and there's a huge sponsor for it because it has a big business value, right, for your company, you may end up buying a GPU cluster and pay for running that application. But otherwise, you'll be taking a commodity distributed system and running most of your applications for data analysis, right? So this chart is basically to argue that it's fine to study what we are studying in rest of the course as in the form of Hadoop, Spark, Google file systems, and so on. They're meant for commodity hardware, small nodes, many machines. So you're not going for a supercomputer, you're going for a large scale distributed system. That's good enough. Now, if you look at the storage side of things, there also you will see similar growth happening, right? You will see that this chart shows you, again, only limited up to 2011, but similar trajectories can be inferred that your storage capacity pretty much has grown 7 orders of magnitude in 33 years, which means you can store very, very large data sets at a reasonable cost. If you look at the memory advancement, even that has shown pretty linear improvement along with storage, right, over the last 33 years, or actually 40 years now. And which essentially argues that you can not only store lots of data in distributed disks across machines, but you can put memory in front of those disks to significantly reduce your average storage access times. So these two charts together argue that given these trends, I should be able to put together a bunch of commodity machines. Each of them are regular machines, commodity, not very powerful, connected over the network. Each of these machines have disks. I can put lots of these machines so that I can have lots of disks and store a large data set. And I can use the memory on these nodes to reduce the storage access time, right? So for most part of your experience with data analytics, you should be happy with taking commodity clusters and building applications on top. So with that, let me get into the storage model and the costing part, right? Again, this is fairly simple. Uh, I'll show you a few things here which you may be familiar with if you have taken the computer organization course and learned about caching. But I'll also talk through a couple of case studies, right? So that you think beyond a computer architecture organization course and hardware level caches and think beyond it. Because any application that you build, any system that you build for data analytics, you should think of caches everywhere. You should think about using memory hierarchy to reduce access cost of storage everywhere. Because you're using cheap storage, you have to think about engineering methods to speed up the storage access cost. And also you're building clusters with hundreds of nodes. So your storage is distributed. So you have to have some techniques to make sure that it doesn't look like system is very slow because you have lots of nodes and your storage is all over the place. All right, so let's look at your data location. And so some of this will be conceptual, but as we get into examples and going forward, as you study some of the cluster technologies, I think this will help to understand the architecture there. So if you look at the location of data, it could be in memory on your. So if I'm running my computation on one of the nodes in my cluster, uh, I would be accessing data from the memory, or it could be in the disk or the storage, or it could be accessible over the network somewhere, right? Maybe I have to fetch data from another node in the cluster because whatever I'm accessing is not locally there on the same machine. Because remember, I'm working with a distributed system. So either your persistent data can be accessed from local store, right, or from a remote store, unless it's in memory. Now, later we will talk about Hadoop, data shuffling, and so on. But let me give you a very simple way to look at this for now so that you understand what use case we will talk about later. Think of a cluster, right? This is a very high level explanation of what Hadoop clusters are. I mean, Hadoop clusters are basically machines where a set of machines where we use Hadoop middleware to run large scale parallel processing applications. Very popular for batch processing. So think of three nodes, right? C1, C2, C3. And there are computations running on these three nodes. And my computation graph is that the C1 is one computation that runs. Then on in parallel to that, on another node, there's a similar computation C2 that runs. And once C1, C2 is finished, then I have to run a third computation, which is C3, taking results from both. Now, let me take an example. Uh, let's say I have a million records of, let's say, sales transactions. and I want to calculate average. Average is not a very good example, and you'll realize later why. But let's take, I want to find maximum. What is the maximum transaction value among the million transactions that I have? And I want to run a parallel application running on a cluster. So what I do is I take my data set. Let me try to put some annotations here. So I had million records, right? So I first break it up. I put 500K records on this machine. I put another 500K records on the second machine. And in both these machines, parallelly, I compute max. So I compute max going through this 500 records, maybe in sequential fashion, right? And here also I calculate max. So I get one value, the maximum transaction value here and here. So you see that I have kind of, instead of running it on one node, I have automatically sped it up or made it double, right? The efficiency, uh, double the performance or speed up. And because I'm taking half the time, I, instead of million records in one node, I have split it up, partitioned it, and run max operations in parallel. Once I do that, I want to take this individual max values and I want to send them to C3, because C3, what it will do is it will take these two values and compute a max of those two, right? So my answer will be at C3 after the finish of C3 saying what is the max of all the million transactions. That's one way to parallelize this whole thing, right? Now this computation looks very simple, but I could be doing much, much more complicated than this, where I take a large data set, I split up or partition the data set into multiple nodes. I do some local computation on these. Then I move around the results to another node and uh, do another computation on that and give the result. Now it happens to be that in this case, all these three computations are same or are computing max, right? So max of these two maxes will of course give me the max output, right? That's my trivial computation example. But way I would run this on a Hadoop cluster is there will be a master node which will basically break up this job into two parts. It will send C1 to, let's say, one of the nodes. And remember that there is storage attached to each of these nodes, right? So this is a data node 1, data node 2. So 500K records are here, 500K records are here. I will run C1 here, I will run C2 here. And then there's a potentially a third data node 3 where I could run C3. Now, in this case, it's very simple that C1 produces only one value, C2 produces only one value, and C3 will do just a max of those two values. Very simple, right? But imagine the computation where C1 produces 100,000 records, C2 produces 100,000 records, and C3 has to process 200,000 records to get to an answer. That means you have to move around data. So a lot of questions that arise, right? Uh, how do we get data local to the computation? Somebody must be moving around data. Then the data is submitted to the master node. Master node has copied data initially to data node 1 and 2. How did it pick these two nodes? Maybe they were the most free, right? They were least utilized, so it's sent there. Now, when they are done, now I have options. I can move the C1, C2's output data to data node 3 and let C3 run on it. Or I can say that let me not copy both these data sets to 3. Let me reduce the copying. Let me run C3 on data node 2 so that data node 2 or whatever the output of C2 was remains here, right? Doesn't need to be copied. So I need only one copy. I need to copy the result of C1 to data node 2. I don't need to copy the data of data node 2 anywhere because it's local anyway. And all what I do is allocate C3 computation to run on data node 2. That could be one way of optimizing, right? So this is a very simple example and a very simple choice. Of course, I will run C3 either on C1 or on 1 or 2. I will not spawn another data node for this because I will reduce copies. But imagine a more complicated set of data processing happening, many partitions of data and a lot of the complex dependency graph, not a simple one like this, you have to make decisions regarding how do you kind of allocate computation and where do you keep data, so that you have to move around data minimum, right? You don't want to move data too much. So essentially, I'm trying to reduce data movement and I'm trying to get data as local as possible. Okay. So we'll come to some of these in more detail later, especially in the case of these kind of clusters and so on. But what I'm hinting at is always when you're running this complex computations, primary thing in mind is that how do I reduce my data access cost? How do I run my computation close to data? So we'll discuss locality of reference as a concept in the next session, but I'm guiding you towards the thought process that always your job is to reduce the kind of uh, uh, data access cost that you will encounter in such a situation. Okay. Uh, Pratik, to your question, I uh, said average would not be a good example because you can try to do some calculation on your own, but you will see that max of maxes will always give you a correct result. But average of averages doesn't give you a predictable result. So uh, because averaging is not a commutative associative operation. So if you take a bunch of numbers and try to partition them into two sets and calculate averages on each of those two, and then take the average of the averages. Now, if you change the ordering of those numbers or you do a different partition, your answer is going to change. So do some calculation and you will easily figure out that average is not a good way to run this way. So we'll get into some of these problems later, because when you partition and do analysis of large data sets, you should know uh, how to partition, right? Because your partitioning strategy should not change your result. Okay, so when you talk about data access over the network, clearly I have to access data over the network here, right? I have to copy data from one node to the other and so on. Some technologies to keep in mind when you are looking at some of these clusters. Uh, you may be familiar with some of these terms, but it's good to at least know what they mean in few lines. Uh, there's a concept of SAN, or storage area network, which is basically saying that if I want to access a remote storage, right? Then there is a uh, basically I can set up some kind of network storage or a bunch of disk arrays, and I can expose it through a specific interface called SAN interface and a specific protocol, and I can have machines, typically servers, access this network storage on a specialized network. So remote storage could be sitting in some disk arrays, right? It could be a storage server, often called a SAN server, sandbox, whatever you call it. And machines, typically servers, will access this over a specialized network protocol. You typically build a special interconnection network as well to connect these two. And these are typically meant for servers because SANs are expensive. So servers typically will access storage this way. So even though I've drawn the picture here, where all these are commodity disks attached to these nodes, it is possible that if you want to build a high-end cluster, these are not local disks. These are disks sitting somewhere else on a SAN server, and each of these data nodes are connecting to them remotely. But that increases cost of the system because SAN is expensive. The other terminology you encounter is called NAS, or network attached storage. This is where it's like, think of a network file server, which you must have used, right? NFS server. So if you have some disk arrays which don't have a very specialized interface like SAN, but this is regular Ethernet, right? And as a client host, like your desktop, laptop, etc., you can simply mount that drive through an NFS like protocol and work with that remote data storage. It's like a remote file system sitting somewhere, right? So uh, these are also useful for storing remote data. So I could have said that in this particular diagram that these are not my local disks. There's a network file server sitting somewhere, and I'm simply mounting that file server volume onto my local data node and doing reads and writes from it. That is another possibility. That is a lower cost. Of course, the best is to have local disks, but if you want to have a next lower cost uh, or a centralized kind of a storage system, but not pay hugely for it, you could have a network file server and connect to it. If you really can pay a lot of money and have specialized storage servers and use a specialized interface, very fast way to access, then you can buy a SAN. But for all practical purposes, when we're talking about clusters here, these are local disks. I'm just showing you options that you may get. Right? So SAN and NAS are little different from LAN. LAN is nothing but connection between within client hosts or with servers, right? This is purely host to host, host to server networking. All right. So again, so cost of access, right? Let's come back to the point of cost of access. So my data could be sitting in memory. My data could be sitting on a storage. My data could be sitting on the network. So going back to my diagram here, I am running a computation C1. My data could be sitting inside memory of data node 1, or it could be in the local storage here, or it could be actually on data node 2, which means I have to copy data from there, right? So three different options and different costs. So of course, the ideal case is whenever a computation runs, data is in memory, right? That's a best way. But then the system has to make sure that uh, highly likely with high probability, whenever the computation accesses data, it's sitting in memory of that node. If not, at least it's sitting on the local disk. Worst case, you have to fetch data from a different node. But if you are able to predict what kind of computation will need what kind of data, you will try to move data locally as much as possible. So for example, if I know this dependency graph, I know C3 will need the output of C1, C2. So before C3 runs, I could make data locally available in memory of the node where C3 runs. So let's say allocate C3 to run on data node 2. I will make sure that C2's output is already residing in memory and C1's output is copied over either to this local disk or into the memory of data node 2. So this is like prefetching, right? So this is why I put down this question that uh, do I copy data directly into memory cache or store on disk? So I have a lot of options. My point is try to hide data access cost. The whole system design is about how do I make data available to a computation when it needs it. So that it's not that when a computation is running, then I'm actually incurring all this cost, because then all this cost becomes very visible, right? Your computation will slow down. So again, three different places where data can be, and there'll be different access times. I mean, you can do some little bit of Googling to figure out that there's a huge difference in cost, orders of magnitude between these three. So ultimately what's happening, you are running a computation and it's accessing some data, right? So you have to understand two metrics for any given layer in the system. So these are layers, right? RAM, then a hard disk, then an Ethernet LAN access to another node. There are two metrics that you should always understand from a cost perspective. I have latency as a metric and bandwidth as a second metric. In each of the cases, you have to kind of evaluate what is the end-to-end latency, what is the end-to-end bandwidth I'm getting. So these two terms, uh, the meaning is very subtle, but you need to understand, right? Latency is if you look at a queue. So this diagram shows you some queue where requests are being put in, and this is uh, the node that is servicing requests coming in the queue. I'm not talking about any computer system here. It's just generally any queue and a processor of the service that kind of dequeues requests and processes it in a very general abstract sense. Now, latency means what is the time taken to serve a request. So I put in a request in the queue. It it kind of goes to the head of the queue, then it is picked up by the by whatever is the processor, and then it gets processed. This time it takes is called the latency. Bandwidth is the number of requests that you will service per unit time, right? Now, often when you actually measure this bandwidth and report it, that's called a throughput. So you can sometimes interchangeably use this term. You can think of bandwidth as the overall pipe capacity of how many requests you can potentially service per unit time, and throughput could be the actual measurement of it, like how many requests per second are you doing. That's the throughput, right? So think of a network bandwidth, right? So I say that I have a 1 gigabit per second bandwidth, but my throughput is 500 mbps because that's what I measured I'm using. And latency is I'm doing some maybe requests or API calls, request responses on this network, and it's taking me 10 millisecond time to service my request. That's my latency. So remember these two terms, because to evaluate your cost of access, these two terms will be the most beneficial. Now, when do you know that a system at any layer has a bottleneck? Because you could be bottlenecked in many places. You could be bottlenecked in memory access, in your storage access, or accessing data from a different part of your network, right? So how do you know where the bottleneck is? A typical way to determine the bottleneck is look at your latency and bandwidth measurements, right? And if you have a relatively high latency, but you have a low bandwidth or low throughput, then you know that something is wrong in that layer. Let's say I'm sending requests to disk and it's actually getting a it's a pretty high latency compared to the average, but my bandwidth is low. That means there's some bottleneck happening at the disk layer, right? So that's why people look at this couple of metrics and try to look at each layer in the system and see as a very ballpark way, right? That is there a bottleneck in the system? Because this is where you're getting high latency and low bandwidth. So we'll discuss more about this in session 3, where we talk about some performance and bottlenecks and so on, and how to avoid some of this. But let's park this thought for now, but at least know these two terms in terms of cost of access, right? Latency and bandwidth. Okay, Pratik, to your question, uh, NAS and SAN. SAN is the most expensive work because expensive option, because there you use specialized uh, storage servers, and it's a specialized protocol. Even the network hardware often is special, but NAS is cheaper. In fact, any network file server you use, that's basically NAS, right? You have basically put your disks on a particular server and use uh, kind of NFS on it, and then NFS protocol on it, and use regular Ethernet to access it. So NAS is much cheaper to do. SAN is specialized hardware, including specialized network. So your server machine that has to access SAN storage may also use a specialized card, not a regular Ethernet card. It's meant for data transfer at a high volume. Okay, so going back to this memory hierarchy. So the point of reducing this cost is to create some sort of a memory hierarchy in the system, right? So folks, there are few people who are trying to join not using their ID. Now, I'm not sure if there is a way to notify them, but I'm not going to admit because I don't know which ID they are using, or they're not verified. So all of you who have joined, if you get a chance to communicate to others, to do so, but make sure everybody joins using the regular bits ID, because otherwise I have to authenticate and admit you separately. Okay, so I was talking about cost of access, right? The way to amortize cost of access or reduce cost of access in any kind of computer architecture you may have studied is by using a memory hierarchy or layers of systems that you build on top of storage, right? Put memory in front of storage. Uh, so this is what you typically do, right? You have a processor, you have disk, and you have memory, RAM, and you put your cache here between the RAM and the processor. And what it does is this is an expensive piece of memory, and you're essentially trying to see if whenever processor accesses some data, uh, whenever the processor accesses some data, it is if it is found in the cache, then it will be much faster. If it is not in the cache, then you have to go and access RAM. If it's not in the RAM, then you have to go and access disk. If it's not in your local disk, maybe you have to go and pull it in from another machine, right? From a network file server or some other data node. So the whole point of doing a cache is to make sure that you have, when the processor accesses, there's a high chance data is sitting here. Now, why do you think this will work? We will discuss in depth in the next session for locality of reference. But for now, uh, think of what you studied in computer organization earlier, that cache is nothing but something sitting between processor and RAM and trying to reduce your access cost and trying to capture some of the data accesses right here. But there's a cost to it because cache memory is much more expensive than RAM, and RAM is more expensive than disk. Now, this is with respect to processors and memory and disk and so on, right? That you study in regular computer architecture organization course. In the modern world, what's happening is almost every layer in the system that you build, you will introduce caches. So there will be network caches that will sit between the disk, right, and any remote store. So for example, again, going back to our diagram, uh, if my data is, I want to access on data node 2, it is not in this local storage, I have to fetch it from a network storage or some other data node. Now, I could be building a cache in between so that I don't have to reach out further into a node that is not near to me, right? So I could be building a network cache which is sitting in between different nodes in my cluster. So you will find in a lot of the system architectures, you will find caches sitting, software caches, not necessarily the hardware ones you're familiar with in computer. Uh, they are prevalent almost everywhere. In fact, some of these are even cloud-based services that you will get. So I'll take a couple of examples, and I want you to kind of study that after this class because these slides will be shared. Uh, and then I can pick it up in the next class again. But I want you to take a look at a couple of case studies. I'll go through them briefly, where essentially I'll talk about certain software caches or distributed caches, which are sitting between layers of your system and that will help to amortize cost of remote access. So let's take an example. These are all for amortizing cost of data access. So I hope all of you are familiar with uh, Elasticsearch. Most of you have heard about it. If not, Elasticsearch is a very popular open source. Of course, it's managed by primarily one company, Elastic, but this is a very popular search kind of tool that can run on a cluster where you can index documents at large scale, and then you can uh, write kind of a search application on top of it. So Elastic has multiple components. It has a user interface, which is called Kibana. It has an API access as well to build applications on top. And if you look at this right side diagram, essentially what happens, and this will run on multiple machines. I'm showing you a picture which looks like a single machine. You have a storage backend where data is stored. Elasticsearch enables you to index the data, right? Because that's what enables in fast searching. That's all sits on some file system storage. Then you have an operating system layer, right? And then you have the application sitting on top. Now, when a user or an application is using Kibana or an API to run searches on the data, then it may happen, especially if it's a cluster, right? That I'm connected to a node and I'm searching, but data is not on that node. Data has to be fetched from another node. And most of the time, this data is actually split across multiple nodes. So definitely some data that you're searching will not be on the local node where you are connected. So how do you make this data access cost lower? You will you'll in fact build some kind of a distributed cache. So what Elasticsearch does is it builds multiple layers of caches. So at the bottommost level, you'll find something called a page cache. Now this, if you have taken an operating system course, you'll be familiar because uh, every operating system, if you especially take a Linux, Unix like operating system, it'll have something called a buffer cache, right? This is meant for file system accesses. So when you access files on your disk, the buffer cache actually stores blocks of data from the file system in memory so that uh, if you are accessing something uh, periodically, then you will find it in memory buffer cache itself, and you don't have to go and read from the disk. So Elasticsearch uses this operating system memory to and uses it for page caching. So as data is brought in when accessed, it's put in the page cache. So if you have a search query that is running and access the same data, it will utilize the page cache. Typically, most configurations, you may actually keep 50% of your system memory dedicated to page caches. Now, these page caches can be bypassed because this page caching algorithms is in the operating system. You cannot change them. So your application could be such that you are not benefiting from the page cache algorithms. So what you can also do is you can bypass them. There are mechanisms of doing that. But the point is that if you are writing data once and keep repeatedly reading data, especially you read similar data or the same data within a time frame, or if you sequentially access data, then it becomes very predictable and applications will find typically data sitting in the page cache. So this we will talk about in the next class more on why should you find some data sitting there in the cache? Why will caches work in the first place? That's a principle of locality of reference and we'll study in the next class. But page caches are basically file system buffers, right, which are used by uh, Elasticsearch. I've given you a small snippet here. This is from my Mac where you can test out the the page cache utility. Try it out on a Windows or a Linux machine, maybe a little different, but there's a mechanism of testing out how page caches really work or file system buffer caches, how they really work. Try this out. Let me know if you're able to see a performance difference in terms of you working with the page cache and without the page cache, even for a regular program. The other two alternatives of caching are called request cache and query cache. These are not operating system level. These are built within the Elasticsearch application. So a request cache is something like, let's say I want to query average sales across all my stores in the last 7 days, and I want to run this every day. Now, definitely when I run it today and look at last 7 days data and report this in a nice chart on the Kibana UI, if I run this tomorrow, again, it's a sliding window, right? Every day I'm running this and looking at last 7 days average sales per day. 6 days is common, right? If I slide by one day, my 6 days are common. So those aggregates are already computed. So the request cache basically helps you to store some of the previous query results. And in cases like this, you can actually reuse results in your subsequent queries. These are very useful for creating dashboards that are kind of changing over time, right? So you're essentially caching query responses mainly for the aggregations you're doing, the results you're storing, that you don't have to go and access the raw data again. Now, there's a mechanism for query rewriting because you have written a query for 7 days on the indices, but actually Elasticsearch now has to modify your query. It has to say, oh, the last day you go to the data indices, but the 6 days you take it from the cache. So in the backend, some query rewriting must be happening. And the last caching option it has is called a query cache, where uh, you want to reuse data not necessarily within the same query, like I showed in the earlier example, but you have multiple queries and they happen to have common data items they're touching, right? So in that case, you may want to kind of store that data in the query cache and make your queries much faster. So cross query caching. Now this Elasticsearch will do automatically for you. So once it parses your queries, it will know what is the potentially common data and it will intelligently figure out whether to do request cache or query cache and so on. But these are mechanisms. And I've given you a reference link. Please go through it. But my point to bring out here is give you some examples of distributed caches. First of all, you have to understand that for any kind of data access, the huge data access system, you have to build caches because otherwise your cost of access is too high, especially in large scale systems, right? So you have to look at opportunities of caching data using a memory hierarchy, putting something in memory closer to where you're processing so that you don't have to reach out to a kind of a backend node all the time, right? That's one thing. The second thing is uh, think outside computer hardware caches, and you should realize that these caches are useful in many cases. So for example, if you're building an application on Amazon, Azure, all these public cloud providers, you're building an application, uh, how do you speed up these websites? You will notice that they give you network caching options. So if you look at Amazon, look for something called uh, CloudFront. Now, CloudFront is a service, just like Elasticache here is for speeding up Elasticsearch queries, and they're doing multiple levels of caching. CloudFront is basically a content delivery network, or in very brief, it's a network cache that you can deploy to speed up your website access, your data access on cloud. And it's a service. You don't have to build anything. You simply say, turn on the caching service, and intelligently the cloud provider will start caching your content, right? So that your users will actually find it faster. So your users could be sitting in various geographies, but CloudFront or this network cache, because it has presence in various geographies, if you're connecting from India or from US and your application is sitting in India, you'd still get fast access from other geographies because caching is happening on remote machines, right? So this is a good area to look into uh, for a system design principle, that caches are interesting. They speed up amortize cost of data access. They help you in good performance in amortizing cost and help you with large scale data systems. And there are many examples. So Elasticsearch, go through this. You can always go through CloudFront as well on AWS. There is another case study I've put in here for Amazon DynamoDB caching, which can use Elasticache, by the way. But you can also use DAX, which is a specific accelerator built for DynamoDB caching. So what I'll do is I'll probably go through this a little bit in the next class again because you're out of time. Uh, and then my plan is, so this is about DynamoDB, last couple of charts. In the next session, since you uh, got an idea of that there are caches and you should use it, we will go through why do caches actually work. What's the reason why they work, right? This principle of locality of reference is what we will uh, go and understand conceptually in our next session. This is the basic fundamental principle why caching actually works in computer systems. Okay, so we'll cover some of this, but I encourage you to, because it's a case study, I'm not going to cover in great depth in class, but please go to this particular blog, read through it. Not everything I will cover in class. These are examples for you to do some outside reading. The objective here is not to understand query and request cache in great depth because Elasticsearch is one tool. but understand basic concepts. So please read through, right? And we'll start here in the next class. And also look at the other references, right? The DynamoDB part, DAX caching, take a look, and AWS CloudFront, you can take a look. Let me just put it out on chat in case you missed the name. CloudFront. Okay. So the links are here. These are links. These are hyperlinks. So I don't need to attach the caching blog here. You will find the links in the deck, and the deck will be on Canvas. I'll post it today. If you find some link not working, let me know. Then I will look for the document again on internet and give it to you separately. Okay. All right. We'll end here. We are out of time. Thank you, folks, and we will continue from here in the next session. And have a great weekend. Textbook, there is look at the latest edition, but this is a fairly old textbook. I would use it only as a reference, not really as a primary textbook. So focus on the deck and the slides I upload and the references I give in class. Okay, you don't need to go ahead and get another textbook. All right, thank you. Bye bye.